Tonight we have the pleasure of having Dave Messier here from TCC, and I'll just give you a quick little bio here and then we'll go ahead and get started. Dave grew up in southern New Hampshire where he got a solid education on construction sites and working on a farm through high school. In 2008, he graduated from Cornell University with a Bachelor's of Science in Natural Resource Management and a minor in business. Dave became interested in energy during college as it was a logical nexus between sustainability and business. Just recently, Dave received his MBA from the University of Alaska, Fairbanks. Using his outdoor education and background, he traveled and worked in Southeast Asia during most of 2009 and managed a small grant with China Light and Power in Hong Kong excuse me, to provide an educational solar and wind system to a youth camp. While traveling in Asia and working in remote communities, Dave recognized the universal need for small energy systems, and after returning to the United States, was given an opportunity to work with rural communities here in Alaska at the Yukon River Intertribal Watershed Council. After 3 years as a project manager for YRITWC, ooh, that's a mouthful, where Dave installed hydrokinetic, solar thermal, solar PV, wind, and energy efficiency projects, Dave moved to work for Tanana Chiefs Conference in 2012 as their rural energy coordinator. Some current projects Dave's working on. He is involved in Interior Regional Energy Plan for the TCC region, combined solar diesel systems, rural biomass projects, and combining passive solar building designs with food production. Dave also currently owns Daylight Energy Services LLC, a company that provides energy efficient LED lighting and solar PV products. Dave is working with ASEP on an organic ranking cycle diesel efficiency project in Tok and is continuing a strong collaboration with ASEP on data collection and different projects. So folks, we have Dave Messier here, and one quick note we just mentioned, like we mention every week, we kind of need to, we'll have a question and answer time here at the end of the presentation, but we kind of need to shoo out of here at about 7:30 because they're going to be having some folks in here afterwards. So without further ado, I gave you Dave Messier.
Thanks, guys. Thanks, Max. So I'm Dave Messier. I'm going to talk a little bit about some of the projects that I've been involved with over the past few years, working with the Yukon River Intertribal Watershed Council. Thanks. And also currently in my position with Tanana Chiefs Conference. First off, I just kind of wanted to get some lingo down. It looks like most folks I kind of recognize, so people have a good idea anyway, but in terms of a kilowatt hour and a watt, kind of one of the things that I learned when I first started doing energy work is you really need to have the basics. You need to know what a kilowatt hour is, what a watt is, just like you need to know what a BTU is and what it's equivalent to. The way I learned it was just via Wikipedia. I got the opportunity when I was doing some work in China to manage a small grant over there, and knew that I wanted to be involved with energy, but I didn't know what a kilowatt hour was. I didn't know what a watt was. So I had to look it all up, and kind of that's how I started the whole process of learning about energy. And I do think that it's pretty important if you're going to go down that road, or just kind of being aware of your own energy situation, if it's in your home or you're working with different your business or what have you. Kilowatt hour here in Fairbanks is basically 10 100-watt light bulbs on for 1 hour. That's a kilowatt hour. It's pretty simple. A BTU is a British thermal unit. It's the energy that it takes to heat 1 pound of water, 1 degree Fahrenheit. And obviously it's important in Fairbanks because we have 14,000 heating degree days up here, which is why we're a really good cold weather testing. And if you turn those BTUs into gallons of diesel or propane, or wood, those are the equivalents up there. I'm not going to read them, but it's kind of important to get a good handle of what all of it means, because as I kind of learned, in some ways I did a little bit backwards. We produced some energy and then kind of got into the details on some projects, when in reality we should have focused on really narrowing down the details before moving on some of the projects. And so they asked me to talk about some of the projects that I've been involved with. And the first project that I was involved with when I came to work with the Yukon River Watershed Council was the Ruby Hydrokinetic Project. Have folks heard of that project a little bit? Yeah? It was a hydrokinetic turbine. There's a picture of it out in Ruby, Alaska. The general idea was, well, we'll put a turbine in the water. It'll provide baseload electric generation for the community. And it'll be able to take over a portion, or a big portion ideally, of their power needs. Well, I did a little bit of homework when I came on, and I came into about I want to say the third year. It had already been installed in 2008, kind of reinstalled in 2009. I did a little bit of work on it then. And then 2010, I found myself kind of in charge of it and didn't really know anything about hydrokinetics. Had a lot of reports that they were meeting with a lot of resistance or a lot of difficulties in the community regarding hydrokinetics. There was just a lot of challenges. No one had really done it before. And so I had just kind of basically come out of my undergrad. I didn't have an engineering degree, didn't know too much about project management, and kind of by luck of the draw, they handed me this project in rural Alaska that had a lot of statewide attention. That was one of the reasons that the Watershed Council had moved towards it, to kind of gain that attention. And in many ways, they kind of did it, I don't know if cowboy style was the terminology that we used. We were kind of lean and mean, low budget project, didn't have any engineers on staff. There was a technology that had been developed by a company that was based in Canada, New Energy, and they had found a site, located a community that was willing to take it on, and come up with some money to put this project in the water. So I did a little homework on hydrokinetics when I kind of was given this project to manage, and found a lot of data on it from the 70s. And then there was this big lapse, and it kind of got taken out of the filing cabinet or whatnot when energy prices increased again in the 2000s. And it struck me as a little bit interesting, why was this 20, 30-year gap where no one had done too much with hydrokinetics? And there's a quote that I really like: before you think too far outside of the box, it helps to be damn sure what's inside the box. And so with hydrokinetics, I'd imagine that they ran into some of the same challenges in the 70s and 80s that we ran into in the 2000s. The turbine that's on the photo there was a 5 kW turbine that we installed in the Yukon River in Ruby. Originally, it was installed really close to the bank. It needs a flow of about 5 meters a second. 2.5 meters a second, I think is what it was, to produce the 5 kW worth of power that it was rated for. And it seemed like a really good idea. You put this, basically an egg beater, in the middle of the river. The natural flow of water will spin the turbine, and it will produce energy. There was a lot of challenges with the project, ranging from how to transmit power from the middle of the Yukon River, 800 feet under a cable, or underwater cabling, over to the shore and integrated into the power supply. Debris were an issue. Moving anything in the river was a big issue. The only device we kind of had available to us that could deal with it was a barge operated by Inland Marine, and that was a really intermittent schedule. We kind of had to go through things along with or kind of arrange our schedule to the barge schedule. And the turbine never really produced that much energy. I think the first year it was in, they had it too close to the shore. There wasn't strong enough current. It was a little bit weak. Second year, they tried to move it out into the middle of the Yukon River in Ruby, about an 800-foot wide river at that point. And it translates into not 800 feet, it was about a half a mile wide in Ruby. And so different areas in the Yukon where they've tried this, they had the opportunity to run a cable across the river, and they could kind of maneuver devices along that cable. In Ruby, we were really, again, at the mercy of the barge schedule. It's a difficult project to install in the middle of the Yukon River. So after 3 years of the project and a number of issues, that was one of the problems we ran into in Ruby. I kind of made the decision to pull the project. Again, this is kind of the first project that I managed. We were underfunded. It was a heck of a challenge to put something in the river right there. This 5 kW turbine, I don't think we ever produced more than 500 kilowatt hours of energy with it, which was a little bit, I don't know, embarrassing or whatever the right term. It was definitely disappointing. That image I actually woke up to. When I was working out there, I slept on the floor in the tribal hall a lot. And one day I woke up and I knew that there had been a high debris load in the river. Kind of poked my head out the window, and you could kind of see down in the river, and I saw this big mass of trees, and I was like, well, that doesn't look good. And then got up a little bit closer to it, and if you can see from the image here, that debris diverter that's in front of the turbine barge, it's made to collect debris and push it off to the side, or not collect debris, push the debris off to the side. That had done, I think, what snowboarders call an endo, and flipped on over and was then accumulating trees and debris. So this was the first project that I had to manage with the Yukon River Watershed Council. They gave me a position. They said, okay, we need to lower the cost of energy in rural communities. Here's something that's already been set up. 2 years of experience. There's a PhD, Brian Hirsch, is working on the project. He had kind of gotten the Watershed Council involved with it. There was a previous project manager who is now working with Ocean Renewable Power Company, another really smart guy. There was another project manager that was a professor at the university, another really smart guy. And we kept running into these challenges. And I guess in the end, it came down to, personally, I don't think that technology is viable for communities, because when you're dealing with communities, it's got to be scalable, and it's got to be something that can be maintained out in rural Alaska. And I couldn't find anybody that wanted to deal with that out in Ruby. And I didn't want to go out and into Ruby and deal with the project, because it was multiple flights out. I think the number I give is 30. That's probably conservative once you factor in all the different folks we brought out there. We had TerraSonde, a company that's located down in Wasilla, go out and do a imaging of the river floor in Ruby. There were problems up the yin yang. We had, I was out there trying to pull the cable out. At one point, we needed a piece of equipment that only one guy in town had access to. He owned it, and he had gotten a moose that day, and he wasn't going out to move that power line until we helped him butcher the moose. So he spent a full day out there helping him cut up the moose, and the next day he moved the power line for us. There were just a lot of challenges with the project. And in the end, I think after 3 years, I don't even know that we produced 500 kilowatt hours worth of energy, worth of electricity. And that was going into the microgrid out in Ruby. They run predominantly about a 175 kW generator out there right now. So this 5 kW was supposed to be the precursor to a 25 kW that was going to take on 25 kW of base load during the summer. Again, the technology, obviously, since it uses open water, it couldn't be installed during the winter. It was something that had to be continuously moved in and then moved out of the river. And so you were really looking at actual production in Ruby for about 5-6 months if you were lucky. So a lot of folks are still working on hydrokinetics and are still pursuing the technology. From my experience with it, I think that it's going to be a few years until they get a lot of the kinks worked out. And with the difficulties that I've run into with it, it's not, I think that there are other technologies out there that are commercially viable, that are simpler to install, that are going to have a lot better success rates, and they're also going to be scalable for rural Alaska. And in my position, that's something that needs to be a big focus, is something that's scalable and something that folks in the community can take on and have the want to take on. If folks don't want to maintain it, then there's no point putting it in, because without maintenance, something's going to fail, it's going to go wrong, and you're going to have to continue to babysit it. So that's kind of what it felt like. This is a picture I actually think I sent to my project manager at one point. We were talking about different debris mitigation techniques and how to lay the cable out in Ruby. So those were some of the lessons I learned off my first project in Ruby, Alaska. You want to keep it simple. You want to make it something the community is going to be able to maintain and take on themselves. And this is a line I really like. You want to be on the cutting edge of technology, not the bleeding edge. And I think in this instance, I think the Watershed Council, myself, the folks that went before me, we were really on the bleeding edge of technology. And it was interesting because talking with different folks involved in the hydrokinetic field, they had the same experiences as we did up in Eagle. Over in Canada, there was another turbine that went in, I believe, on the Ross River or another river in Canada. And it was a little discouraging because the technology was I think, designed more for a more controlled river system. And the applications we were trying to put it into were obviously not a very controlled river system. And so the engineers that designed it didn't design it for any of the real-world challenges that you'll see if you're trying to implement this project specifically in rural Alaska, which is where it makes the most sense because you've got the highest energy costs. And so that's, again, kind of you need to, if you're doing projects in rural Alaska, you need to really be you're very cognizant of some of the challenges that you'll run into and very realistic about some of the challenges that you'll run into. Another project that we were involved in was the CCHRC home up in Anaktuvuk Pass. Folks have probably heard about this home. They've got R60 walls, I think, R100 in the lid, really good insulation on the ground to protect the permafrost below it and to keep the pad that they laid down from shifting or cracking. And the Watershed Council installed about 800 watts of solar and then also a 600-watt wind turbine, or what we thought was a 600-watt wind turbine in the back. And this was another project that I kind of inherited and got involved with through the Watershed Council. It was an excellent opportunity to kind of get our name out there, and that's why my predecessors had gotten us involved with the project, and it was excellent to work on, but again, a project that didn't necessarily have some of the thought that should have gone into it go into it during the planning stages. So an overview of wind. It's really specific, site specific. Folks have probably seen pictures of all the turbines that are going in on the delta. Most of those need at least a year's worth of data, wind data. Somebody goes out, sets up a wind anemometer, collects data for about a year, and they go back and analyze that data, process it, and determine if you've got a good site or not. Some of the turbines in the delta, I believe they're the big one that AVEC is putting in a number of locations is a 100 kW north wind turbine. The AEA, Alaska Energy Authority, has estimated the costs for operations and management and maintenance of those systems are about $20,000 a year. And if you think about the delta, generally you think flat. And a conversation I've had with a lot of folks is, you know, you put in a 100 kW wind turbine in the middle of the Yukon Delta, and for the folks that are living in the community, it's the highest thing on the horizon. These aren't necessarily folks who have experience climbing 200, 100-foot towers, doing operations and maintenance on these turbines. And another kind of, I guess, one of the issues on a community scale we've run into is that, you know, you need a large crane to actually install them. And sometimes those cranes are 6 months to a year out. And so, again, a really good technology. The reality of it is for my region in the interior, we don't have a very good wind resource. And I have a bad, I guess, experience with wind because of the operations and maintenance needs on the turbine that we installed, the small turbine we installed in Anaktuvuk Pass. And also just, I guess, the community's involvement. Again, once you have moving parts in a community, something's going to break down. Just like your vehicle, moving parts, something's going to break on it one way or the other. So operations and maintenance has got to be key. And for a lot of the systems that I work with, a lot of the communities that I work with, there's been papers that have been put out by AAA, by different entities in Alaska stating that one of the #1 issues with working in rural Alaska is the operations and maintenance. The reality of it is folks will transition out of positions. Maybe you had a really strong person, a community champion, taking on a project one day, and then the next day something happened and they're out. They're no longer in the community, they're no longer in the position, what have you. And so it's a difficult environment to work in. So I guess one of the focuses that I've run into or that I've focused on is trying to minimize, make things as seamless as possible. Wind integration of that small system, again, it was a small turbine, a 600-watt turbine, or so we thought. Ampere sells it as a 600-watt turbine. In actuality, when you connect it to the grid, it turns into a 300-watt turbine, which we got an independent assessment of it about a year after it was installed that said, hey, by the way, this 600-watt turbine, and it's only 600 watt when the wind speeds are about 27 miles an hour, is actually only a 300-watt turbine when it gets connected to the grid. And so once you have a 600-watt turbine that turns into a 300-watt turbine, your energy production has definitely decreased pretty dramatically. On the integration side for that specific turbine, it came out off the turbine head as wild AC. There was a shutoff at the tower base. Then there was a rectifier that turned it from wild AC into DC, inverter that turned it from DC into AC, and then it went into the home electrical system. And wind is exponential, so it increases exponentially, which is great if you have a better wind resource than you thought, but it's pretty poor if you have a worse wind resource than you thought. And so the folks that had originally thought, hey, this is a great idea, let's put this into Anaktuvik Pass, I don't know that there was a lot of data from the wind resource Anaktuvik when they made that decision. They talked with folks in the community who all said, you know, Anaktuvik's one of the windiest spots on the North Slope. It'll be a great spot for a wind turbine. Well, in actuality, when I took hold of the project, I did a little Google search and came up with this report from the Alaska Energy Authority that stated Anaktuvik Pass actually had a Class 1 wind resource, and so it was not the best place to put a wind turbine. So we had this system this small wind turbine up in the middle of the Brooks Range that cost about $12,000 to install. It was supposed to be a 600-watt wind turbine. It turned into a 300-watt wind turbine. And then we didn't have the wind resource that we needed. So this is my second project, my second energy project, working with the Watershed Council, and I kind of, that's why I put, oh shit, right there, because it was, again, in my mind anyway, you know, we're supposed to be producing power, we really weren't. So it was a real bummer. And just like that hydrokinetic turbine out in Ruby, I think the number that I set on that was $700 a kilowatt. This, I think we pulled it, maybe it had produced 200 kilowatt hours after a year, but I don't even think that that was accurate. I think that might be high because we had issues with the integration. There were different components, and some of the components didn't talk to one another correctly. And this is a problem with some certain small systems. You definitely want to make sure that you have a system that is skookum when it goes out, that all the components work. We had a system that had kind of been, to some extent, not scabbed together, but not properly tested before it went out in the field, and we purchased it from the vendor thinking that it was a system that had been properly tested. And so we had a number of integration issues. The inverter we couldn't get to talk correctly to the rectifier, and it really wasn't as simple and as easy. And I was looking at it. We had an electrical administrator out there, maybe not an administrator, but someone with about 20 years experience in the electrical field. He tried to give us some guidance on it. He couldn't figure it out. We were on the phone with Ampere, which was an English company. So they're 10 hours off of Alaska time, I believe. Trying to figure out how to do all the integration, et cetera. We came up with some problems, needless to say. That's not to say that wind doesn't work. It definitely works, and it's being shown to work down in a number of areas on the coast. I think in the right applications, it's a great technology. But in the interior, in my communities, I've had a not so positive experience with it. And then there's also, if you look at a wind map of the interior, it's not that great. It's not very windy. I've talked with a few folks down in Tanana, and they say, oh, hey, it's real windy down here. And I'm like, I don't know if you guys know what real wind is. And that's kind of one of the other issues that I run into with folks who are really up on traditional knowledge, but just kind of not connecting that to the reality of what you need to make a wind turbine viable. Because Tanana, it might be windy by interior standards, but by Alaskan standards, it's still maybe a class 1 or 2. So again, kind of lessons learned from that project. Keep it simple, stupid. Do your homework before you go out and you try to install a project. Make sure that you've got all the information that you need. Really be up on the system before you decide to fly to the middle of the Brooks Range and install it with folks. And then be wary of manufacturers' claims, unfortunately. That's kind of been an ongoing issue, specifically in the small wind market with different manufacturers that have been out there. They had made claims. There wasn't a really good testing laboratory that tested those claims, so manufacturers could to some extent make the claims that they wanted. And NREL finally started testing some of those claims at a wind research site. And and proving some of them wrong. So again, so the Ruby hydrokinetic project and the project we did up in Anaktuvik Pass were both during the summer of 2010. It was a pretty busy year. And at the end of the summer, it was also for me, I guess, I'd kind of failed in a couple of ways in my mind. I was a little bit down, a little bit stressed out. I think I got a bunch of gray hairs that summer. And then towards the end of the summer, we had the opportunity, we had further project funding to do another project. And so we wanted something that was close to Fairbanks, because flying out to Ruby and flying out to Anaktuvik Pass is a great time. But once you're doing it every other week, it loses its appeal. And so we worked with our community down in Tanana, the Tanana Tribal Council. And this is the back side of their Teen Rec Center. And we installed a 20-panel solar PV array down in Tanana, and then 2 panels of solar hot water. And then what you can't see is the heating controls that we installed in the building. When they built this building, it was a Denali Commission grant, so grant money, and the mechanical administrator that designed it decided to put these balance valves in. And I mention this because it's often the things that you don't see that really make a difference. And so these balance valves, I actually talked to the same consulting company that had done the plans, and I asked him about the balance valves, and he said, you know, I guess I've never really seen those work correctly. And I was like, well, why the heck did you put them in? And that was just what they had spec'd, and no one questioned them on it, and so that's what went in the building. So I think this building was constructed in 2007, and we did some work on it in 2010. And what we did was we installed zone valves and setback thermostats, or programmable thermostats in the building. So previously, because nobody knew how to operate the zone valves, and by the mechanical administrator's claims, they didn't work that well anyway, what ended up happening was the heat was on full blast 24/7, 365. So it was okay in the winter when it was -40, and they'd also kind of undersized the system. There was someone that had come in and done like a free evaluation for it, and he looked at the 2x6 walls, he looked at the building, and he looked at the amount of baseboard, and he was like, wow, there's not really enough baseboard in here. And so during the winter, if you've got it on full blast 24/7, it's okay, it'll keep you heated. During the summer, you need to open a window, and diesel's getting expensive, and you really can't afford to burn it. So we ended up going in and crawling around the crawl space, installing those zone valves and programmable thermostats so people had more control over their comfort level in the buildings. Now, a balance valve, you need to take off the side cover of a baseboard heater unit, a radiator, and you need to adjust the balance valve. On a programmable thermostat, which ideally a maintenance person will do, on a programmable thermostat, people are a little bit more used to. You can go to the wall and simply adjust it. And those are connected to the zone valves, which allow heat into the radiator system for each specific room or each specific zone. These were all kind of things that I learned at the time, so it was really a learning experience for me. But on the PV side, we installed it in 2010 for about $5 a watt, and again, it was for a nonprofit, so I think we were probably a little bit below what going market rates were, but not too bad. $5 a watt, I think, was a pretty good cost. And we used N-phase microinverters, which were really new at the time. Now, in Ruby and in Anaktuvik, one of the biggest challenges that we came up with, despite the fact that the system didn't work that well, was also monitoring. I can't tell you how frustrating it was dealing with these tiny little wires on a Campbell Scientific data logger up in Anaktuvik Pass that were supposed to go to this main bus bar, which was controlled by a technician down in Oregon, I think, or Washington State, trying to figure out which little 18-gauge wire went to which spot on the bus that he could connect with, logging in through this Campbell Scientific data logger. Really a kind of a difficult thing to get right. Ended up we had connected one of the wires wrong, which is why they couldn't report on it. Even after they started reporting on it, some of the information was wonky. He couldn't figure out quite what it was. And so as a project manager, in a perfect world, you want to be able to hit a button and you can see what's going on with the system you just installed. That was definitely something that I did not have in either Ruby or in Anaktuvik Pass. In Tanana, we found the right system, I think, for the job, and we installed these micro inverters, N-phase units, and I went online today, clicked a button, and each one of those panels showed up, and it showed me what those panels were producing real time. And it's also important to note that In the first month of this 20-panel solar array, which costs about $20,000 down in Tanana, we produced more energy than we had in 3 years in Ruby and in 1 year of wind in Tuvik Pass. So for me, that was I guess definitely helped shape. I don't want to make any, I definitely don't want to not acknowledge that. That had an impact on me because I was in the middle of 3 projects. 2 of them I considered really frustrating and to some extent a failure. And the third one, it was producing power. And, by my definition, I guess a decent amount of power. And so this is the Tanana solar monitoring. I went online today, took a screenshot of it. You guys can see there's a number in each one of those panels. It's a mock-up of the building. In each one of those panels today at whatever time I went on, 3 o'clock or so, is producing that many watts on each panel. And it's really important to note that in the last 3 years, I had about 3 hours of operations and maintenance on this system. So if you compare that to the Ruby turbine, which I couldn't walk away from, or debris would pile up on it, and I'd have to, just banging my head against the wall, or the Tuvik Pass turbine, which, we definitely weren't perfect in that. We had manufacturer issues. We had a lack of knowledge. We had a poor wind site. But I don't know if you guys can imagine, take those 3 projects in comparison, which one's better? Solar, in my mind, won out hands down as being the best bang for your buck and more importantly, the least operations and maintenance. And again, you really want a system in the bush that you can walk away from. 3 hours over 3 years, I'll take that any day of the week. And you can leave it up 24/7, 365. We haven't touched this. I think I was down there just by happen chance and brushed snow off of it once. And it's most of the power that's been produced on it over the lifetime of the system down there, it's produced 10 megawatt hours. No one's touched it. It's just been producing energy every day that the sun comes out that's not covered in snow and sending it into the building. So for me, kind of taking all of those considerations, all of those previous experiences into account, it was definitely a winner. And again, much simpler installation. With the solar, we use a microinverter, which can be installed on the back of a panel. So all of the wiring is in AC. After you get past the inverter, there's plug-and-play connections. So easier than plugging in a keyboard into the back of your desktop computer because they actually click together, so you know you did a good job. And then right after you leave the inverter, it's AC wiring, which is a challenge, or which is beneficial because most electricians have been working with AC wiring for their whole lives. Very few of them have been working in DC. And so when you deal with different solar systems, it's a different thing for folks to get their heads wrapped around that in a traditional solar system, you're dealing with DC. In DC and AC, they're not too much different, but again, if you've had an electrician who's been working on an AC system for his whole career, making the jump to DC can definitely be a challenge. And certain electricians, not all of them, have a little bit of hubris, and so they're afraid to admit when they need more education on something. So by making all of the wiring right off the back of the panel AC, you simplify things quite a bit, you make life easier, and more importantly, you make it scalable or successful in a community. So in Tanana, the PV array that I wish I had a pointer, but the PV array that we installed, it's got a decently long payback because we don't pay too much. Tanana's on the GVEA grid, so 5-year savings are about $4,400. It's kind of convenient because in most parts of the interior, you can predict that a 1 kW solar array is going to produce about 1,000 kilowatt hours per year. So 1 kW of installed capacity translates to about 1,000 kilowatt hours of production over the course of the year. And you can see I try to break it down relatively simply. You've got the cost of materials to install and then the 5-year energy savings. So which, I guess, technology that we installed had the best payback or saved the most energy? Anyone? The thermostats. The thermostats. But I show folks this picture, and that's not what you see. You see the sexy renewable energy. You see the solar PV and the solar thermal. But if you look at the data, which a lot of contractors really don't like to do, you see which technology had the most bang. You get the most bang for your buck out of it. In the long run, we saved, I think every 5 years, I think every year we're saving about 1,000 gallons of diesel, which is a really significant savings when you look at the cost of materials. And albeit, you know, that to do that to another building, it would probably be more expensive to install it, but not by 5,000 gallons of diesel over 5 years. There'd still be a heck of a payback. That $2,000 that we installed those zone valves for, that was pretty much, we didn't really charge for our labor, I guess. But that's, I mean, to me, looking at the data was really significant. And seeing, you know, at the end of the day, it wasn't the renewable energy that had the biggest impact, it was energy efficiency. And it might not come to the surprise of some of you, but for me anyway, I guess I go to conferences down in Anchorage and here in Fairbanks, and everyone says efficiency first, efficiency first, efficiency first. But no one, in my experience, really does it. And I was one of those people. And so after we completed this project, I was like, wow, numbers don't lie. So I kind of decided to start spending a little bit more time on efficiency because I think that is what's going to have the biggest impact out in the communities. So lessons learned from that project: efficiency first. Remote monitoring is really key, especially if you're going to be reporting to funders and also back to the community. You don't want to go to a community meeting and when people grill you, well, what's that producing? You kind of throw up your hands and say, I don't know. That's not good. And then operations and maintenance. Costs can be kept low, keep them low. Talked about the wind turbine up in Anaktuvuk Pass. Again, you know, we may have had a negative experience with it, but once you compare the operations and maintenance, I mean, more than 12 trips up to Anaktuvuk Pass, trying to figure out, diagnose what was wrong with that system, to, you know, 3 hours total labor over 3 years down in Tanana on that solar array. It's, you know, if you're comparing two different technologies, both of which produce energy, for me anyway, I wanted to go where I didn't have to babysit anything, where I could put a minimal amount of time into it. And for me, that was energy efficiency and solar. So Anaktuvuk Pass, that was another project that we received a grant for. Worked with the Nunavut Corporation, the Village Corporation, up in Anaktuvuk Pass. Originally, they wanted to do some wind, and I said, I don't think that's a very good idea for this community because of their wind resource and my previous bad experience with it. And so we put together a proposal and submitted to the Department of Energy for energy efficiency on their community buildings or on their corporation buildings. And we did a number of different buildings, but the one that I guess I'm the most proud of is their shop. They had a regular picture like something the size of about Smart Automotive or something. A big, I don't know, 8,000 square foot shop that you can drive a dozer into, and they lit it with these large high bay lights that you'll see in the top right there, 400 watt HPS, high pressure sodium high bay lights. And the thing about those lights is if you turn them off, you've got to wait about 5 to 10 minutes for them to light back up. And so I don't think they ever turned those lights off in the shop because somebody went out for a cup of coffee, they were working in the shop, and then they went back and they didn't want to wait 5 minutes, so it wasn't their money. It was a lot easier to turn those lights off. Somebody left for the night. Well, they didn't want to walk back in the next morning and be sitting in the dark for 5, 10 minutes, so they probably left those lights on. And so we had a couple different options. A lot of folks were suggesting we go with T5s, which to some folks are still kind of the new technology. They're an improvement over the high bays for sure. But looking at what else was available, it didn't seem like they were that much of a savings. I did the math out, and this is important. These calculations are important because all of you guys can now go be energy efficiency engineers because it's that simple. People ask me if I'm an engineer all the time, and I say nope, but I did fairly well in multiplication and division in 5th grade. And so that's really all it takes is just kind of an inquisitive mind and basic math. We took those 12 400 watt HIDs, multiplied them out. It was about 4.8 kW, and we figured those are on probably 6,000 out of 8,700 hours a year, and they're probably going through about $7,000 worth of electricity each year. And compared to the T5 scenario, we could have cut their costs by about $1,500 or so. But we decided to go in the end with LED high bays on that shop. And they're instant on, instant off, just like the T5s, but those high bays use significantly fewer watts. And we kind of did that against this was in 2000 and, I think it was in 2012. It may have been just last year that we finally did this shop. We had done their grocery store previously and changed that all out to LEDs and had a really good success with it. And so against some folks' better judgment, folks down in Anchorage do a lot of lighting changeouts, we decided to go with LEDs. And the savings were very significant. And that's the one we chose. And those were their electric bills. And again, for me anyway, going from, I was probably didn't do so well with 2 projects, did okay in the 3rd project. I didn't have the most winning record of successfully saving energy out in the communities that I was supposed to serve. And once we did this project, and this was only 1 building, we really made a decent impact. And I moved on from the Watershed Council and haven't kept up on the bills, but these are straight from North Slope Light and Power, undoctored bills. They were seeing monthly energy bills of anywhere from $700, $800, $900 a month. After we did the change out, I didn't see any bills that were above $200 a month. So that was a significant savings, and more importantly, because there's not too many buildings in Anaktuvuk Pass, I'd argue that this one change out kind of changed the load profile of the generator in Anaktuvuk Pass just a little bit. This is just 1 building. In all of the buildings that we worked on, I think it made a big difference overall. And those are the results from some of the change outs that we did. They had in the restaurant there, you'll see a really significant savings because the restaurant had taken, the restaurant that the corporation owns up there was an old SKW construction camp. And when most construction firms go into a community, they want something that's just ready to ship in and slap together. So they used all electric heat, all electric appliances. It was a fully electric restaurant. They just had and bunkhouse, and they just had to plug it in. So we did some efficiency work on the windows, replaced the windows, which were previously much worse than some of the car windows that I've seen. We replaced the single-paned, aluminum-framed windows with triple pane, higher efficiency fiberglass windows, saved them a bunch of money in electric heat. In the shop there, we went to all LED lighting and then were able to put a few of the lights on sensors, saved them a bunch of money and energy there. In the store, we swapped out all of their lights, which were T12 fluorescent lights and 40 watts each, to LED, 15-watt LED lights. And I usually show a picture of it, but I've got two pictures, one taken before the swap out and one taken after. And you can see just a significant difference in the amount of light that's in that building. And it's a store, so they're obviously trying to light up their product as much as they can. And folks they made the comment after we did the change, they're like, man, I'm going to need to start wearing sunglasses in here now. And the really rewarding part was I did some calculations and figured just an estimate of how much their lights were on. We did the change out, and I was actually in Panama when I got an email from Toby, who is the accountant of the North Slope Light and Power. He sent me the bills. I put them into the spreadsheet, and they had reduced their consumption for the first month almost exactly the amount that we had predicted. So it was really rewarding, and again, I mean, the numbers don't lie, and those are all taken from project numbers and from kilowatt hour reduction that we saw from their bills. And then at the bottom, I've just got, and this isn't a direct comparison because at different load capacities on the generator, you'll have different efficiencies, but their stated efficiency on the PC and the power cost equalization reports is about 13.8 kilowatt hours per gallon that they get. Their efficiency of transferring that energy that's in diesel into electric energy that they can send over their grid is about 13.8 kilowatt hours a gallon. And at that, by the numbers that I came up with that were, again, from observed results, we saved about 30,000 gallons over a 5-year period, which is about $240,000. And that cost of materials is about $38,000. So a significant payback there. And these were just a few of the buildings out in Anaktuvuk. So for me anyway, it opened up a world of possibilities if you could start to do this on a larger scale to a number of our other communities to most buildings in the community, you could really have an impact of changing the load profile in the community just by switching to higher efficiency products. And then you can start to really make an impact when you do your renewable energy. And so I went back, and actually, after I had that really successful project in Anaktuvik Pass, I was like, man, I need to start selling these, because I went around town, and the best price I could find was over at Tesco or at Crescent Electric, and they wanted like over $1,000 or $1,300 for a high bay. It was just outrageous. So I ended up contacting some suppliers and starting to bring up LED lights on my own, because I saw what a great energy saver they were. So knowing what I know about LED lights, I went back and I was giving a presentation to a meeting that happened here in Fairbanks about biomass in October. And I was, again, I'm on this crusade now, trying to change people's mind that solar, renewable energy, although it's sexy, it's not where you'll get your best bang for your buck. So I went back to this photo and I looked at it and I was like, wow, that's probably a 75 watt high pressure sodium light. And in my business, I would change out a 75 watt high pressure sodium light for a 20 watt LED. And you get about the same amount of light, longer lifespan, et cetera. And so for outdoor lighting, they're on an average of about 4,000 hours each year. And so when I did the math out, I realized that if I just changed one of those lights, I basically had the equivalent of one of those panels each year, which again was, I don't know, a little bit mind-blowing for me. I was like, holy cow, what in the world were we thinking? You know, if I knew then what I knew now, the things I would have done differently. And if we had gone through that whole building and changed out all of their lights to more efficient lighting, we would have easily saved more energy than we could have produced with the solar project. And so the difference between producing energy or saving energy is pretty extreme, because when you're saving energy, you're removing the max load from the grid. If you go through, and it's not so applicable in Tanana, but if you go to another of my communities, Ruby, for example, or Galena, and you put a 200 kW solar system on the grid, in the middle of summer, when that solar array is producing 200 kW, your generator is going to be running at maybe 50% capacity. And with spikes in the generator, not with spikes in the generation, but if a cloud goes over, that 200 kW could drop up or down pretty quick. If you remove the potential load from the equation altogether, you can then change the size of your generator, which is really significant out in rural Alaska. And that's why folks are going through and doing things like changing out street lighting. At TCC, I'm really pushing changing to LED lighting. Obviously, I'm biased, I also sell it, but I'm trying to keep the two pretty distinct and not sell any of the lights. I'm just like, they're a great product, and folks should start using them in tribal halls and stores, et cetera, because they save energy and they'll save diesel. So again, down at the bottom, you'll see the installed cost per panel. We did that system for about $20,000, which breaks it down, so each one of those panels is roughly $1,000. Had we installed one of those lights, it was about $300. And that's installed. So another thing I like to do when I'm giving this presentation, just to kind of bring home how much easier it is show of hands in the audience. How many people have installed solar or wind or solar thermal? Got one hand? One hand over there, so what's that, 3? Maybe 4 in the back. Raise your hand if you've ever changed a light bulb. There you go. So it's a lot easier. And that means that it's a lot easier for folks in my communities to do. So I've brought up trainers, run classes on how to install solar. It's great. I think renewable energy is excellent. But at the end of the day, you're a lot more likely to screw up a solar installation than you are changing a light bulb. And a lot more people out in the communities have plenty of experience changing light bulbs than do putting in solar systems. So this is I guess the model that we're pushing at TCC with all of our rural communities. Really, you need to go through, collect data, and plan. It's not as sexy. Definitely fewer people like doing it, but it's incredibly necessary. And then you need to focus on efficiency. And you need to look at your electric loads and then also your building shell. And then finally, after you've done all that, then you can move into renewable energy. Then you can move into producing electricity with solar, producing heat and BTUs via cordwood. But it's really important to follow those steps, because if you don't, you'll probably, maybe suffer some of the same headaches and heartaches that I did with my first projects out in rural Alaska, or even at your homes here, and you'll eventually come to acknowledge that this is probably the way you should have done it. So I'm trying to save everybody who's listening a little bit of heartache and a little bit of trouble. So kind of one of the projects I'm working on or trying to push right now is up in Manly Hot Springs, putting that model that I just talked about into practice, and kind of what does that mean. So Manly Hot Springs, they're a really independent group of folks in the tribe there, and they've got a tribal complex that's located about a half a mile away from the electric grid that's owned by TDX in Manly. If you drive into Manly, they've got a kind of a complex of buildings on the right-hand side about a half mile before you really get into town. And they've got their own diesel generator out there, because one of the guys who was working there got a sweetheart deal from Army surplus and installed it. They wired up all their buildings and started plugging in electric load. So he got a 35 kW generator, which realistically only runs, or used to only run at maybe half of that load. I went out there and kind of looked at it, and I was like, wow, this is kind of a wacky system, because they were carrying all this excess generation capacity for really intermittent loads. And in the meantime, they were going through 17,000 gallons of diesel each year to run their generator, which was a lot of money. Even in Manly, where it's only maybe $5 a gallon or less delivered. Anytime you transport diesel, you've got costs associated with that, and you've also got environmental hazards associated with that. And so they finally got some money after I've been kind of trying to talk to folks for about a year or so. I happened to make a phone call up to them to try to get them down for a biomass conference. And they said they were in the middle of doing a generator change out, and that an entity had gone out from town, and they sized their generator. They looked around, and they were like, you could probably get away with half of that. You could probably get away with a 15 kW generator over here, a 12 kW generator. So they bought one, sent it out, and then it didn't work all the time. So they're like, oh crap, the company said, we undersized the generator. I think you guys need twice that. So they ordered a 30 kW generator. So they were going to go from a 35 kW down to a 30 kW generator, which would have been more efficient for sure. But I got a hold of them and I said, no, you guys don't need to do that. You really need to look at your loads. And so I just verbally over the phone kind of walked the guy that was out there, Mike, through some of their loads, and I knew they had electric heaters, which is one of the stupidest ways of producing heat or using electricity that I know about, and most inefficient. Had electric heat. They had 9 kW worth of electric dryers, 4 kW worth of relatively inefficient lighting, a double coil 3 kW worth of electric water heater. And so some of these things are probably not totally unlike what you guys need for your homes. But the difference is you're not living out on the grid off the grid where you need to supply your own electricity. These guys out of Manly were. So I said, let's look at some of the ways you can replace these. And he was like, well, we need to have dryers because we run a laundromat. What are we going to do with that? And I had talked to somebody because I had the same question when I went out there. I was like, geez, what else? What other drying capacity is there? Anybody got any ideas? Propane dryers. What a novel idea. So we swapped out their 9 kW worth of electric dryers with a couple of propane dryers. And now they don't need to carry extra 9 kW of electrical capacity on their small microgrid. We also took out their electric heat. So when you produce electricity, most folks have probably heard your car engine is only 30% efficient. Maybe a really efficient electric or diesel generator is about 50% efficient. And so once you're translating diesel into electricity and then sending it over the lines, they say electric heat is 100% efficient. And it is, in terms of translating the energy that you get off the outlet into heat. What they don't mention is that the actual production of that electricity is, maybe less than 50% efficient. So a Toyo stove is about 90% efficient, right? So they were keeping a 35 kW generator going to run 6 kW of electric heat and losing a lot of efficiency just to turn diesel into electricity and then back to heat. So we swapped out their electric heating, and I'm talking electric baseboard, which are great. On the up front, you get a 4-footer for probably $40 over at Home Depot of electric baseboard. it's super if you live down in Anchorage or down in the Pacific Northwest where you don't have as cold extremes and you've also got cheaper electricity. But up here, it's really silly. Then we also looked at their electric lighting or their lighting and talked about the possibility of swapping that out from the high-pressure sodiums and the fluorescent lights they had to LEDs. And then we also looked at their 3 kW or 2.5 kW, I forget what it was, electric water heater, which would kick on now and again. And their 3 kW electric water heater, which I think was maybe an 80-gallon water heater or a 120-gallon water heater, you know, somebody had one lying around and they plugged it in. That was heating water for a mop sink and maybe a shower. So they were keeping 80 gallons of water or 120 gallons heated year-round, 365, 24/7 for a sink and maybe a shower. And this was at the tribal hall, so nobody used the shower there. So we swapped that out with an on-demand propane heater as well, and we removed that 3 kW worth of electric heat from their grid also. They also had a big compressor in their shop that would keep kicking on intermittently, so you never knew when you had a big spike. And so we got them to unplug that unless they needed it. And we focused on efficiency. And we brought their max load previously was pretty close to 35 kW. And we took out the 6 kW of electric heat. We took out the 9 kW of electric dryer. We're working on the 4 kW of lighting. And we took out their electric water heater. And all of a sudden, their 35 kW load that they needed to have capacity for went down to a 6 kW. And I think it's important to bring this up because I look at Manly Hot Springs Tribal Council as a miniature village. They've got a lot of the same loads that a much larger village, say a Tanana, a Ruby, Fort Yukon, et cetera, would. And so, you know, I realize that maybe in every community you can't decrease their load through efficiency by almost 50%, but I think you can get pretty darn close. And that's a significant amount of savings if you just focus on efficiency. So I'm really excited to be working with Manly. And after we focus on all of those things, and we're still in the process, then, just like the plan said, then our goal is to add some solar PV to the system. They've already got battery storage, and I know if we keep focusing on efficiency, we can definitely get them to turn off their diesel generator for probably at least 6 months a year. I think we can get them to turn it off from March until October if we focus on efficiency first and put in a solar array that can keep those batteries charged and minimize their phantom loads and then also their nighttime loads. I'm pretty darn sure that we can get them to go way down on their electrical consumption, and we can turn Manly Village Council's diesel generator off, which again, I'm really excited about because I see it as a bit of a microcosm or what have you for what's possible with other communities. Something that again, it's like another tagline, but something that I learned firsthand. There's no silver bullet. Energy efficiency in rural communities is going to take a combined approach. So there's a lot of folks out there, a lot of utilities who are currently getting big sums of money from different funding pots, Department of Energy, the state of Alaska, et cetera, to do different generation or better transmission, et cetera. And those same utilities, they don't have as strong a focus on actually saving energy. And from my experience, if you spend some of that time and energy saving energy, you'll have a much better bang for your buck, and it'll be a much more efficient system and a much more sustainable system in the long run because you'll be able to use smaller generators, you'll need less diesel to run the generators, and then you can integrate your renewables more effectively. But for me anyway, and I keep stressing the energy data, I wouldn't know what I currently know if I didn't keep track of some of the numbers on the projects that I've worked on and managed. The ability to accurately quantify the results from the projects that I've got has really led me to come to these conclusions. And for example, on the topic of solar, I'm kind of having this ongoing conversation with somebody down at Alaska Energy Authority who's kind of down on solar. And he gave me, for example, I think 3 lines of data from a project that was installed out in Caltech, a solar project. And so I've installed solar both through the Watershed Council at TCC, I helped with the project, and then through my personal business. So I know that solar can be viable, and that PV Watts, which is a solar estimating calculator, which is available through an NREL website, is very accurate. And so the person down at AEA sent me some data on a project that was installed out on Caltag, which is in my region. It's the interior, so I know the numbers are going to be pretty similar. Sent me 3 lines of data: energy production for October, energy production for November, and energy production for December. And said, look, these numbers are really low. Solar is not viable. That was all you had, a monthly energy production. And I said, you don't have a problem with a bad technology, you've got a problem with a bad install. Because from my experience, the numbers that PV Watts gives you are very accurate. And I can't tell you how amazing it is to be able to go onto a website, type in some data on a community, and the government's already done all the legwork of integrating different weather stations, et cetera, and it gives you a printout of what your monthly energy production should be for that zip code that you've put in. And in my experience, it's been conservative. And that ability, you don't need a year's worth of wind data, and sending somebody out with an anemometer that's not cheap, getting data, bringing it back to Anchorage, dealing with remote login, et cetera. You can just click some buttons online and go to any zip code here in Alaska, and you'll get an estimate of what that site can produce in solar electricity for a year. And I found it to be amazing. And so when the person from AEA sent me those 3 lines of data, I was able to send them back 3,000 different cells of data from the Enphase install that we've got down in Tanana that say production for each day of the year. And I just took a year's chunk. And that data was a little bit more convincing to him, I think, than the 3 cells that he sent me, sending him back 3,000. So data is really important, and being able to prove and quantify when a technology is viable is really important, because with renewables, you're changing a mindset. And for me, that's been a big part of it, changing the mindset, which is just revolved around diesel in rural Alaska and cordwood for the last 50 years since villages were created or were established, and changing that mindset and saying, there are other ways or other technologies, but you need to be able to prove that and make other folks see it. So energy independence out in rural Alaska, in my mind, leads to healthy communities. And that means getting the community members involved to do work on the projects. And so that means that folks need to work together. In some communities, you've got different tribes that are at odds with the city, or maybe someone's nephew or uncle had a bad experience with a school district and they don't work together. That's going to lead to failed communities. And in some communities, it kind of already is. And so getting people to work together to put their differences aside is a phenomenal and a necessary step, because local energy can create jobs. And that's being done right now with biomass out in Tanana. Hopefully this summer we're going to have a small solar install out in Ruby, and we'll be able to hire folks from the community, because again, it's not rocket science. Everyone who can turn a ratchet can put up a solar array with the right guidance. And then it's got to be simple, and it's got to be easy to work with. When I started at Tanana Chiefs Conference, I had a meeting with our president, Jerry Isaac, and he just kind of stressed to me, he was like, Dave, if it's not simple, people don't give a shit. They're just going to go with diesel. And I couldn't have said it better myself. The reality of it is there's a lot of subsidies out in rural Alaska, and people know what they know, and they've been doing it for 50 years. And I'm sure just like a lot of folks out in the audience probably, folks are adverse to change. And so you've really got to create something or come up with something simple. Otherwise, you're going to have a Ruby hydrokinetic turbine on your hands where there's not buy-in from the community. You've got a different technology, and nobody wants to deal with it. And kind of by association, nobody wants to deal with you. So I also wanted to touch really quick on Tanana's biomass project. Bear Ketzler is the city manager for Tanana, and I think he's been over there since about 2006. And it really, he's a bit of a role model for me, I guess, because I see some of the work that he's doing out in the community, and I think it's the standard that ideally everyone should be following or should be pushing towards. He's installed a number of garn boilers, and he's putting local woodcutters to work. Again, kind of a low technology. Anyone out in the village has experience cutting wood and knows how to do it. Folks are harvesting their own energy. And the number that he likes to toss out there is when he started, the city was importing about 30,000 gallons of diesel each year to heat their shops, to heat the washateria, and to take care of mostly heating. They don't run the utility out there, so it's almost all space heating in their community. I think in 2013, he's on track to consume about 12,000 gallons of diesel a year. And so the difference, about $72,000 in fuel, has been replaced by 150 cords of wood. And that's represented a gain of about $37,000 for folks out in Tanana. There was even the folks from Stevens Village, Bear likes to tell the story, floated down a big raft. Folks from Stevens Village, which is north of the Yukon Bridge, floated a raft of firewood down to Tanana. People are kind of hungry to supply. If there's a need and it's something that they can make money on, out in rural Alaska, there's a definite incentive to do it, and people are doing it. They floated a raft of 80 cords down to Tanana and sold it to the city, which fired their boilers. They're heating all their water for the washateria. They're just putting a system on the school, and more importantly, they're able to keep that money in the community. And it's something that's scalable. Folks have been working with cordwood almost their entire lives, or a lot of people their entire lives. It's something that's familiar to people. It's not as big of a technology change as are some technology leaps, and they're having a lot of success with it. And again, just being able to keep that, even if it's just $37,000 in a community, it ties back, in my mind, to community health. You know, if folks are just given an opportunity, if a teenager in Tanana can go out, instead of getting in trouble, he knows if he goes and spends his time cutting wood, he can bring it in, fill up a box, and the city will cut him a check, and that means something. And I think it's going to help cure some of the social ills if we can make that a little bit more mainstream in some of our communities. I just did a really quick estimate, and I think the 42 villages in the TCC region probably collectively consume well over 5 million gallons of fuel each year, which, if you translate that into cordwood, at about, I can't remember if I used $250 or $300 across the interior, that could translate into over $12 million worth of economic development. The current model is the barge comes in, you know, fills up your tanks, you pay the barge guy. It's either going in Crowley's pocket and BP's pocket, getting shipped out of state to their corporate headquarters. They're down in Florida or down in Houston, et cetera. That money's coming in and then going right back out. Steve Hagenson has this really good rain bucket model where he talks about rain going into the bucket and then being filtered out. Well, in this model, in the current model, money's coming into the village and it's just going right back out to pay for energy costs. If we can keep that money in our community, and that's a big goal of mine, then we build stronger, healthier communities, and biomass and homegrown energy are great ways to do that. Again, just in terms of the health of a community side of things, this is a spill response for oil. I don't know where this photo was taken. I just found it off the internet. Some folks maybe have been on site for a spill response. I never have, but just about everyone's probably been on site for a biomass spill response. It's a lot less toxic, a lot easier to clean up. Just kind of like to draw that comparison. And then moving forward, one of the projects that we're trying to get going with a company that has previously done a lot of work with military bases, and they're now a subsidiary of, I believe it's Nanacorp. Folks probably remember a few years ago the military kind of had this big push to go green because a lot of their forward operating bases, a lot of their fuel trucks were getting hit going to their forward operating bases. They couldn't run their generators, et cetera. So this is one of the companies that responded to that, and they had this idea, if we can just do demand side management, right size the generators, factor in some batteries and do some renewables, we can make a generator, we can make a fuel truck supply a forward operating base, you know, maybe not just for a week, maybe we can make it supply the base for 2 weeks. So if you can half the number of fuel trucks you've got going on enemy roads or in, you know, dicey territory, that's a big point for the military. And so there's a lot of overlap between what this company did in Afghanistan and Iraq and also down in Antarctica and what could be done here in Alaska. And so moving forward, I think this is going to be the model that wins out, and I know a lot of folks at ASEP are already working on similar kind of microgrids, focusing on renewables integrated where they can and being able to have some sort of buffer so the generator can handle it, right size the generator. And I think a big part of this is dealing with some of your efficiency first, so that you can actually have make good projections and lower the usage on the grid, and thus your renewables are going to go a lot farther. But they use smart controls and can actually control different loads remotely to turn on and off. So if they've got, you know, if they have their batteries start going down, they can switch off loads that are less demanding. So if they've got a water heater that's trying to pull, I don't know, 3 kW worth of electricity, and they've got some other needs that are more pertinent, they can actually prioritize using some of their controls to say, look, that water heater can switch on when we've got the available capacity. In the meantime, it's going to stay off. And a big part of this is just, again, collecting the data, knowing what your loads are and where they occur, and thinking smart about it and being able to come up with a system that's planned correctly from the get-go, and moving forward in that way. So I think that's about the end of my presentation. Hopefully it was useful for folks. If anyone's got any questions, feel free to ask.
Have you done any geothermal project?
I haven't done any geothermal projects personally.
Have they looked at them in the villages?
Yep. Do you mean geothermal for electric production or geothermal for geothermal heat pumps? Heat pumps. They have what they call a coefficient of power, which is basically your return on your investment. So a geothermal heat pump is a lot like a simple, I mean, almost like a refrigerator. If I can make that comparison, and that you need a compressor to pump refrigerant or liquid through condensers, which are basically in the ground and trying to get some of the heat. And so coefficient of power is kind of a return on your investment. So how much electricity are you putting in versus how much heat are you getting out? And so in the data that I've seen, the numbers aren't quite there because electric costs are so high is one of the reasons. And then also there's really high cost to drill a well out in rural Alaska a lot of times. So I kind of wanted to dive further into it and actually work on a project, but thus far I haven't been involved with it, and that's, I guess, one of the reasons.
Break even here in town.
What's that?
In town there it's break even, and the electricity that's the big deal. Is the electricity costs so much to pump the fluid.
Yeah. And again, just like, you know, I've never had an experience with it, I guess, so I can't speak directly, but similar to how it was difficult, or it can be difficult to work on a turbine if it's up in the air, it can be difficult to work on even a coil if something goes wrong and it's down in the ground. And so, you know, that's kind of something that, again, trying to keep things village scale. And in my mind, it kind of makes a little bit more sense right now to put more of your energy towards building a tighter building shell. That said, I know that there's been some really good work out in Canada that they're still getting data back on using just simple coils rather than digging, you know, punching in a well, doing a shallow well. You can do it with a bucket of a dozer or something like that, laying in coils. I think they use PEX tubing, not more than 10 feet below ground, and then using that to preheat incoming air. And I think they were actually working with some more efficient heat pumps. And so it'll be really interesting to see what Bear Ketzler and I think Thorsten Klupp was working with them on that, come up with. But it's definitely not something that I'm opposed to by any means, but just those kind of were my initial forays into it, and I kind of turned back and focused on other areas.
People are using Rankine cycle electrical generators. You know, using the heat from the ground or heat from a hot spring. Well, in Manly, for example, you'd have some heat from the ground, and it would be possible to generate electricity from that. I mean, these units do exist. They've been produced by Pratt & Whitney and Boeing.
Yep. And again, just like wind, some of those technologies are very site specific. Manly does have a good resource. Different communities don't always have the, I guess, the human resources, or at certain points the capacity to manage a project of scales that might seem really reasonable sitting here in Fairbanks, or, you know, just like that turbine probably seemed like a real good idea if you were an engineer sitting down in Alberta where it was designed. Once it gets put into play, there are certain challenges that, you know, that may not have been anticipated. And so I'm not averse to geothermal and organic Rankine cycle turbines. I think what Bernie's doing out in Chena Hot Springs is great. I think his project out in K&K Recycling, doing basically, you know, organic Rankine cycle energy production through burning cardboard. I think those are all phenomenal. for me, I guess it's focusing on projects that I know will build buy-in and be successful, or at least have a high likelihood of being successful out in the community. That's kind of where I've chosen to spend more time and energy. And so I think ORC units are great and they have great potential. But the larger a project gets out in a rural community, to some extent, the more moving parts that it has, there's more failure points. That's, again, kind of why I like solar.
What is there any way to engage kids, you know, in terms of the education, in terms of secondary education or whatever? I mean, you said that you know, the power of money is pretty damaging, and so there are all these grants and various facilities and various instrumentation which can be purchased instead of learning about it. Is anybody out there in your experience learning about it or teaching it?
Teaching specifically about the technology?
Well,
or?
teaching, getting a technology degree, or technology, not a degree, but technology, you know, encouragement, technology exposure, so that there can be some help, you know, from the younger generation.
Sure. I kind of try to walk I guess, a fine line between being realistic and being pessimistic sometimes. And so, you know, I mean, I think those are all ideas that have been talked about and that are talked about a lot here in Fairbanks, down in Anchorage, and in the communities. They're all best case scenarios. This is what we should be doing, and I completely agree. I think that's definitely what we should be doing, and there are attempts at that. The reality of it is, in a lot of schools out in rural Alaska, there's a high turnover with teachers. They don't stay in a position for too long, and the folks that do, to some extent, there's teachers out there that already have a very heavy workload, and so adding certain things into the curriculum, what it comes down to is finding a teacher that's willing to be a school champion on that project and willing to work it into their existing workload. And so I've made different attempts at that and had not much success. And that's not to say that it can't happen. I think it needs to happen. It is the way forward. That's, you know, again, we've got a limited amount of time and energy, and it's where can you, in a realistic sense, where can you try to spend your time and energy that you're going to see the best returns? So it's not a perfect world, and there's not a perfect scenario, but I definitely agree that that's where more energy needs to be spent. And I think I believe there's different folks. I know there's different folks that are working with energy efficiency in classrooms and energy education. I try to tie it in whenever I can. I've got a photo that I didn't include when we did that project down in Tanana. I went over and presented to the science class and gave them a tour of the solar panels and talked to them a little bit about the project that we'd done, and was ideally going to try to team up with the science teacher and get them to go over and take a more active role in monitoring, et cetera. And the reality of it was kind of follow through never happened one way or the other. Other things came up. He already had a booked schedule, et cetera.
Thank you for this presentation. I worked for a state senator for 8 years in Juneau, and we have had overview after overview on many different types of energy projects, renewable, I mean, you name them all. I mean, from growing algae to heating up the center of the earth, bringing the hot water. But so this has made more sense to me than anything, and I've been saying for years that this is what we need to focus on, is efficiency, and we need a bigger campaign for efficiency in the state, and would like to see that. And I don't know if you ever gone to Juneau to do your presentation, but you know, as we have tried to get people to see kind of what rural Alaska is really like living in a small village. I mean, I grew up in Yellow Hot Springs. So in regards to the hot water, we were told by experts that the water's not hot enough. We would have to bring in a lot of those plants to make it hotter, and they're very expensive, and you know, the maintenance is pretty high. So that's probably not a good idea for a lot of these communities. But, focusing, of course, on efficiency is a good idea. And then, looking at local resources as well. And, you have, the biomass in a lot of those communities. So I think it would be a great idea if you could go down and present, to some of the legislators. Might be a little bit late now, but maybe look into it next year, where we can start, it's just always educating folks. We have a lot of legislators, of course, who don't even live in, or have even gone to rural Alaska. So they have no idea. When I worked for the state senator, we did go down to Ruby and look at that project. We stopped in Tanana and looked at this project. I was a little disappointed with the Tanana project because there wasn't a lot of previous planning, and they could have been doing a lot more with getting more energy, I guess, to more places, but they're so isolated, in back of the town where their boilers are. So I think, planning for sure is a great idea, but I would just really encourage you to educate more legislators. They're the ones that are making the decisions to where the money goes. And in regards to, buildings, we have engineers, we have people going out and pretty much railroading folks in the communities because they're engineers. They can pretty much put anything in the communities, and that's one thing that we have really been trying to get folks to it's really hard for folks in the community sometimes to override, what engineers are saying. We're the experts, they come in, this is what you need to do. And so they get a lot of projects, a lot of buildings that aren't energy efficient or don't work right. So, we have seen a lot of that in a lot of the communities. And there's nightmare after nightmare in a lot of the communities. Getting these huge projects that they can't afford. They can't afford to run them.
Yeah, and I completely agree, and I really appreciate the comment because next Tuesday I present in front of the Senate Subcommittee on Energy, and then on Wednesday I present in front of the House Subcommittee on Energy. So thanks for that vote of confidence. And then in regard to efficiency, as I just said, we don't live in a perfect world, but TCC at its convention last week, we kind of Tanana submitted a resolution, and TCC now has the highest building efficiencies standards in the state of Alaska. They're kind of building to a passive house standard, similar to what Thorsten Klupp has been doing here in town. R70 walls, R100 in the lid, and R50 in the floor. That's a resolution that TCC passed, and from what folks know about TCC, resolutions sometimes get passed, but following through with them is always the challenge. So we're going to try to be pushing that, but it is on the books, and so that's something. Sorry, I just wanted to say, and I think your comment about engineers going into a community and kind of prescribing what they think is right is extremely accurate. And it's one of the biggest frustrations that I have. And that's why, I guess, from my school of hard knocks, I've got no problem talking to AA and saying, you're wrong. So, depending on the project, because they're not always wrong. They're sometimes very right.
Well, there's, all of these different, Denali Christian and even the Alaskan Tribal Consortium. It's really sad.
And they're all great people, and everyone is very well intentioned, and the projects are great. But when I go to Hughes and see two pumps that are in tandem that are each 10, I think they were either 6 or 10 kW pumps, and I get a nudge from someone next to me that says those shouldn't both be running. One of them is backup, and then you do the math, and that one that's running that doesn't need to be is costing $14,000 a year in energy costs. And so, again, who designed it and what communication was there with the folks who are operating it? Did it occur, et cetera? But those are the kind of things that, best of intentions could end up costing a community in the long run.
One real quick question. When you say, the kilowatt hours have a refrigerator and freezer running, what does that equivalent to?
It all depends on the refrigerator or freezer that you've got. There's a great example when I went down and I had the ability to take a class through Solar Energy International, and there was an old timer who lived in a bus, who was one of the instructors, who gave me this example of some older woman had asked him to design a solar system that could offset all of her electrical needs. And he went in and saw our electrical needs, and it was like, oh my God, this solar system is going to cost you $150,000. He said, and I went back and I prescribed to her different efficiency measures. One of them was a refrigerator, and just replacing old, outdated appliances. And then after she did all the appliance work, I think they installed a system for $20,000 that could take on all of her electrical needs. So it really depends on the refrigerator. There are some great numbers online, and always look for the Energy Star model. And I don't have, I mean, one of the numbers that I've seen was like 1,200 kilowatt hours a year for a refrigerator a year, but that really depends on the size of the refrigerator, et cetera. So it's a difficult thing to answer.
Well, I think that's all the time we have tonight, folks. But thanks very much for coming out. If you'd like, we can hang around afterwards and ask some more questions you have, Dave. And Dave, I think you did a great job.
Cool.
Thank you very much.
Thanks, guys. Thanks for having me.